Hi everyone, this is Virginia here with Practice Exam 1A. This is just where I'm going to go through all of the problems from Practice Exam 1A and hopefully explain and clarify how to approach these. My email is here in case you need to contact me or if you have any questions. And I just want to let you guys know that you've been preparing all semester for this exam and you got this. You can do this, okay? So keep positive, okay? Okay, let's get into it. So for the first question, they want us to pick out some features from this reaction coordinate diagram and answer some questions about what's going on in the reaction. And so the first component they ask us about is the delta E. And so we know that the delta E is going to reflect the difference in energy from the reactants here on the left to the products here on the right. And so if we sort of think about where we start from the reactants, this is going to be an input of energy for the products. So this is going to be endergonic because energy is entering and it will be a positive delta E. Okay, so just by comparing those two energy states, we can eliminate answer A and answer E. Okay. So next they're asking us about activated complexes. And I just want to remind everyone that an activated complex is the same as a transition state. Those are just synonyms for the same thing. And these are our high energy states. These are the strange molecules that don't really exist, where the reactants are kind of twisted into funny states that you could never isolate on your own. So these are at the high energy peaks. So at point B we have an activated complex, which is the same as a transition state. At point D we have an activated complex, transition state. And at point F we have an activated complex, or a transition state. Okay, so it looks like we have 3 of each of those. Okay, so we can eliminate option B. And so now, for the intermediates, these are real molecules that are made in the process of a reaction. Molecules that exist on their own, but that get used up later on in the reaction and end up disappearing. And these are at the valleys, like at point C and at point E. So we have 2 intermediates. Okay. So this reaction overall is 3 steps, as indicated by the 3 humps that have to be overcome. And so the correct answer here is C, because it shows our 3 transition states and 2 intermediates that we counted. Okay. So in step 2, we have a nuclear, or in problem 2, we have a nuclear fission reaction. So the idea behind fission or fusion is that everything's trying to become iron 56. Okay, so if you're greater than iron 56, you're going to undergo fission, like this uranium is doing. And if you're smaller than iron 56, you'll undergo fusion to try to become iron. And so to balance these reactions, it's pretty simple. We just want to make sure we have the same number of particles on both sides of the reaction. So here they've given us all the mass numbers, But what I'm going to do is go through and fill in the atomic numbers for the atoms. So uranium is, if you look on the periodic table, it's number 92. Okay, so I'm just going to mark 92. This neutron will have an atomic number of 0. That's true on the right side also. And then we have strontium, and strontium has an atomic number of 38. 38. Okay, so we can add the tops for the left and the bottoms for the left, and then do the same for the right and figure out what we're missing. So here on the left, for the top, we have a total of 236, and then we have a total of 92 for the bottom. On the right here, we have 3 of these neutrons, so we have a total of 93 on the top, and then just 38 on the bottom. So we can see what we're missing on the right. If we just look at the difference between these two sides, we can see that our unknown element is going to have a mass number of 143, and it will have an atomic number of 54. And we can just call it X for now. Okay, so we're just trying to make sure we have the same number of atomic particles on both sides. And if you go to the periodic table then, we want to look for what this atom is using this 54, because it's the atomic number that tells you what atom we have. And atomic number 54 is xenon on the periodic table. So the answer to this question is going to be xenon 143. Okay, and that's option E. Okay, so don't forget about paying attention to the 3 and the balanced reaction, etc. And don't forget to use your periodic table, because that's a useful tool. Okay, so we have another nuclear question. So this time it's about the types of decay that atoms can undergo. So I've gone ahead and put this table on the screen here. And if you want a slightly more detailed version, go to the ebook. It's in chapter 31 and part 2, and it's a table on there with some of this information and more. And so I've written here the 3 types of radioactive decay that we generally think of in Chem 112 and some of the things about it. So we have alpha decay, which emits a helium nucleus or an alpha particle. And elements do this if they're really big because it's an efficient way to get rid of material. And they do this if their atomic number is greater than 83. Okay, so big things do alpha decay. For beta decay, we emit a beta particle, which is like a nuclear electron. And this is when we turn a neutron into a proton. Okay, so we end up seeing beta decay increase the atomic number of atoms. And its opposite is positron emission, where you give off this anti-electron and you turn a proton into a neutron and shoot out this positive particle, thus decreasing the atomic number. So you do beta emission or beta decay when you have too many neutrons. And so it's too heavy, and you can see this by comparing the mass of whatever isotope they give you to the mass on the periodic table. And if it's bigger than the periodic table mass, then that means it has too many neutrons, it's too heavy, so it's going to turn a neutron into a proton to try to get to a more balanced ratio of protons to neutrons. Then for positron emission, you have too few neutrons. So your mass is less than the periodic table mass. And so what you do is you decrease your atomic number. Here you're going to decrease your atomic number to reach that more balanced nucleus. So if we go through the options here, so the first one says beta decay results in the conversion of a proton into a neutron, and that would be positron emission. So that one's out. For B, positron emission increases the nuclear charge of an atom. So that's like the atomic number. And that's not true either, because we're actually getting rid of a proton. So we would be decreasing the nuclear charge. So that's not right. C says nuclear decay always follows second order kinetics. I wrote down here that all of these follow first order kinetics. Okay, with nuclear, just always first order. The same kind of first order stuff we talked about earlier. Always first order, so that one's not right. Okay. D says gamma decay produces high energy radiation. And we think about all of these decays being really high energy reactions, and the energy that they release we call gamma radiation. And it is a really high energy form of radiation, and that's why there's always in comics and cartoons someone gets hit by gamma rays and something crazy happens. And so D makes sense. For E, though, it says alpha decay decreases the atomic number of the parent atom by 1. And that doesn't make sense because it would decay it by 2. Okay. So D is the right answer because gamma decay is, by definition, the release of high energy. Here we have a problem that I think kind of fun. We have the method of initial rates, where they give us this table of data where they run 4 different experiments with 4 different concentrations of reactants and are looking at the reaction rate. And we're doing this to figure out what order the reaction is in terms of the different reactants. And so what we can do is look at if we change A concentration, but keep B and C constant, what happens to the reaction rate? And then we can look at the order. So we can do that by comparing experiment 1 and 2, because there we've doubled the concentration of A, but B and C are staying constant. And so when we double the concentration of A, we can see that the reaction rate here is doubling. And so when we double, triple, quadruple the reactant concentration, and the reaction rate does the same thing, then that's first order. Okay, so we know the reaction is first order in terms of A, because when we doubled A, rate doubled. So I'm going to go ahead and put a 1 there for the A. And then we can use the same logic for B. So if we want to see what happens when we change B, we can compare experiment 3 to experiment 1, because then we've doubled the concentration of B, but A and C are staying the same concentration. And then if we look at the reaction rate, when we go from experiment 1 to experiment 3, there's no change in the reaction rate, even when we double B. And so what that tells me is B has no effect on the reaction rate. And so this is going to be 0 order. And then to compare how C affects, we're going to compare experiments 3 and 4, because that's where A stays constant and B stays constant between those two, but we've doubled C. And when we look at then what happens to the rate between experiments 3 and 4, the rate quadrupled. And so we doubled concentration, quadrupled the rate, and so that's going to be second order because it changed with the square. If we had instead tripled the rate, or tripled the concentration, we would have done 9 times to the rate. Okay, so we have all the orders now, and usually what we do is just exclude anything that's 0 order, because it's not doing anything anyway. So we can get rid of that and just say Ka times C squared is our rate law, and that matches option C. And this rate law tells us that overall it's third order. Okay, and we'll need to know that for the next question. Okay, so for the next question, they want us to figure out what the K is. And you have some options for this. You just want to pick any one of the experiments. So pick your favorite one. Doesn't matter which one you do. And we're just going to plug in the rate and the concentrations and do the algebra to solve for K. So I'm going to use the first one. So we have 2.0 times 10 to the negative 4th molar per second is equal to K, which we're trying to find. And I'm going to plug in my concentration for A, 0.40 molar, times my concentration of C, which is also 0.4 molar. Oops, going off the squared. Okay, and so when you do the algebra there, you solve for K with your calculator. You get that K is equal to 3.13 times 10 to the negative 3. And then you go to look at your answers, and you get a little stressed, maybe, because there's two options with that number. The only difference are the units. Okay. For those of you who have interacted with me in person, you know I love units, so this is exciting. But so let's think about the units. Here on the left, we have molar per second. On the right, we have K. And then we have 3 molar, so we have like molar cubed. So if we solve for K by just moving the molar over, we would have molar divided by molar cubed divided by second. And so this is the same then as saying like 1 over molar squared times the second. Okay. And so the right answer for this one is going to be A. And these are the units for any third order reaction. And the other units that we have here are for any second order. Okay, so here we have a pretty typical integrated rate law problem where we have acetaminophen, also known as Tylenol, and we're looking at how it's removed from the body. I'm sure you all have taken Tylenol before. It's not good to take if you're over 21 though, because it can react with other things in your body. One thing in specific that people above 21 worry about. Okay. Anyway, so they give us some data about this reaction. They say it's first order half-life. So that's an important thing, which is why I underlined it, that it's going to be first order. And the first order half-life expression is on the data sheet. It's at T1/2 is equal to 0.693 divided by K. Okay, and that's right next to the second order half-life expression on the data sheet, so make sure you know the difference between them. Okay, so they tell us it's 3.2 hours, so I wrote that below. The initial concentration is 15 microliters per mil at 1 p.m. when the student takes the medicine. And I want to know what the concentration will be 7 hours later at 8 p.m. Okay, so what we're really trying to find is the concentration of A sub T. Okay, and so here we're going to use the integrated first order rate law, which is on your data sheet, and it's this. It's the one with the ln. So we have the ln concentration at a given time is equal to the natural log of our initial concentration minus KT. So if we look here at the left where I've put all of the data, we know T, we know A naught, we're trying to find AT, so we need to have our K value. And our link to K is going to be this T1/2. So we'll call our half-life up here 3.2 hours and solve for K. And when you do that, you get that K is equal to 0.2166. And then I just left the unit in terms of hours because the time they give us is in terms of hours. So just make sure it matches. Okay, so we have our K. So let's start plugging things into our equation. So we're trying to find the ln of A naught sub T. We're starting with the natural log of our 15 microliters per mil. It's a weird unit, but it's concentration. Minus our K, 0.2166 inverse hours times the 7 hours that are going by. So if we plug everything from the right side of this equation into the calculator, we find that the ln of a sub t is equal to about 1.192. So how do you get rid of a natural log? With an x, or with an exponent. Exponential? Is that a thing? Okay. I think that's funny. Okay. Anyway, we're going to do e to the power of both sides to get rid of that natural log. And so we'll have a sub t, which is what we care about, equal to e to the power of 1.192, which ends up being 3.29. And our unit on concentration is just going to be whatever we put into our equation initially, which is the microliters per per mil. Okay, so make sure you guys can identify the different equations for first order, second order, and I think it's really useful to organize your data like I did here on the left. Also, I didn't mention this at the beginning, but hopefully you guys are working through these problems with the calculator that you're going to have on the exam. Okay, because there's a lot of people who can just crush these problems with their graphing calculator, but as soon as they have to be a little more careful with the orders of operation on the little dinky calculators, you end up getting the wrong answer. So just make sure you can recreate what you're doing on the smaller calculators too. It's better to make those silly errors now than when we're in 100 Thomas taking the exam. Okay, for number 7, we have a nuclear question, and it's asking which is most likely to undergo fusion. And fusion is coming together, which is why, like, when they talk about fusion cuisine, it's always like two cultures coming together into one hopefully delicious restaurant. And so with fusion and fission, everything is trying to become iron 56. Okay, and so if you're smaller, it makes sense that you would come together and try to add up to become iron 56. And so anything smaller is going to undergo fusion. And so here this is a pretty quick problem with the answer being A, because everything else is bigger than iron 56, and this would undergo, instead they would do fission, splitting apart to become that iron 56. And then iron 56 is just chilling, so. Okay, so here we have another integrated rate law problem where we're looking at ethanol decomposition on alumina surface. So they tell us that this is a second order process. So I just like whenever they tell me the rate order to underline it. Okay, they give us the K right out there with 4 times 10 to the minus 5th molar per second, or molar inverse, second inverse. And we're at 600 Kelvin. Say we're starting with an initial ethanol concentration of 0.5 molar and want to know the concentration after 8 hours. Okay, so let's go ahead and write our second order integrated rate law equation. We have 1 over AT is equal to 1 over A naught plus KT. Okay, so they told us the temperature, but temperature doesn't come into this equation at all, so we're just going to ignore it. Okay, so we have we're trying to find A sub T. We have A naught, we have K, and we have T. So we can just go ahead and plug into this equation and solve for a sub t. So we'll have 1 over that is equal to 1 over 0.5 molar that we're starting with, plus our K, which is 4 times 10 to the negative 5th molar inverse, second inverse, and then we have so many hours. Hours! Oh no! We can't put hours into this because we have seconds as our K. We have seconds in the K, so we need to change our hours to seconds. And so we're going to do some dimensional analysis. So we have 8 hours. In 1 hour, there are 60 minutes. And then in 1 minute, there are 60 seconds. And this equals 28,800 seconds. And so this is going to be the T that we use in our integrated rate law. Sorry, I'm going to move all this over, running out of room. Okay, so we have 1 over AT is equal to 1 over 0.5 molar plus 4 times 10 to the negative 5th molar inverse, second inverse, times 28,800 seconds. Okay, so now I'm going to say something that you will probably ignore, but it can be nice to write your units into your calculations, because then as you're writing, you realize that you can't put hours next to seconds. They have to be the same. Okay. But anyway, this 1 over AT, when you solve everything on the right, you get 0.317. And then if you do 1 over that, I got ahead of myself. I'm sorry. Okay, when you solve everything on the right, you get that it's 3.152. And so A sub t is going to be equal to 1 over that. Which is going to be this 3.17 molar. Okay. And so this matches pretty closely to answer E, which is the right choice. Okay, so again, make sure that you organize your information. That'll help you see what goes where in the equation. Watch your units, and make sure you can solve this problem on the same calculator that you'll have in the exam, because you can't have a graphing calculator during the exam. So here we have a kinetics problem where they give us a plot, and we can use information from the plot to think about what's going on in this reaction. And so to figure out what order the plot is, we start by looking at the axes. So we have time on the x-axis and the natural log of A on the y-axis. And so the integrated rate law that has the natural log in it is going to be the first order integrated rate law. And so we can look at that equation to help us understand this plot. So the equation is the natural log of A at some time is equal to the natural log of our initial concentration minus KT. And this equation can be thought of as a linear equation where we have y and we have b plus mx. Okay, so this 0.4 for the y-intercept is going to be equal to that b component, which is equal to the natural log of our initial concentration. And the slope is going to be equal to negative k. Okay, so using the slope, we see that k is just equal to 0.073 seconds inverse, which is also a hint that this is a first order equation. Okay, so then they want us to figure out the half-life, and we do have an equation for first order half-life, where T1/2 is equal to 0.693 divided by K. So this will be 0.693 divided by 0.073 seconds inverse. And so T1/2 comes out to be about 9.5 seconds. Which corresponds to answer C. Okay, so make sure you're comfortable with taking the integrated rate law expressions and thinking about them in terms of the lines and what the slope means, what the intercept means, and what should be on the axes. So here we have a question about beta decay. So let's just stop and think about what beta decay is. So this is the never pinch a buffalo thing, but it's where a neutron is converted to a proton and a beta particle is emitted. And so this results in an increase in the atomic number. And this happens when we have too many neutrons. So we have to kind of get rid of one and turn it into a proton to make the nucleus more balanced and stable. Okay, and so the way that I approach these problems is to look to see if the mass number that's given to us on the isotope, if that's greater than whatever the mass on the periodic table is, then it will undergo beta decay. Okay, so let's go ahead and write the periodic table masses here. Okay, so I wrote the rounded periodic table masses there. Okay, and so now we can compare the mass numbers on the given isotopes to the periodic table mass numbers. And so for the hydrogen, the mass numbers pretty much match. So that's the stable isotope. So it's not going to undergo any sort of decay. For B, we have nitrogen, and its mass number is smaller than its periodic table mass. So this wouldn't undergo beta decay, it would do positron emission instead. Carbon-14, the 14 mass is greater than the periodic table mass of 12, which is the stable isotope. And so this would undergo beta emission. Let's look at the other ones. For neon, again, we have the mass number being smaller than the periodic table mass, so that would do positron emission. And the same goes for the uranium. And so we can look at the equation for carbon-14 during beta decay. Do a better job. So we have carbon-14, which has an atomic number of 6. It emits a beta particle. And now, to balance this, we'll have to have 7 protons. For 14, the mass number stays the same. And then we can look at the periodic table to see that that's nitrogen. Okay, so this is the beta decay reaction that it would undergo.